going to study about regular perturbation as applied for boundary value problems. Now, obviously, this technique has a whole lot more applicability than just 2-point boundary value problems. But in this particular lecture, we're going to focus on using regular perturbation for BVPs. Let us consider this particular BVP. So y double prime plus 2 epsilon y prime minus y equal to 0, subjected to y0 equal to 0 and y1 is equal to 1. So it is defined on the domain 0 to 1. Now we see the presence of a small parameter epsilon, and usually physical problems are defined in terms of various dimensionless parameters. For example, if you are studying fluid flow, you will end up with the Reynolds number. It may either be high or it may either be low, and depending on what the magnitude of Reynolds number is, we know physically that you will either have what is called a Stokes flow, or more generally called as high Reynolds number flow, which encompasses boundary layer theory or turbulence and all these things. So this kind of a physical bifurcation, if you like, because of the presence or rather characterization of the equation through a parameter is quite common in various aspects of physics. And so if epsilon is small, can we do something about this equation? Well, in this particular case, the equation is not at all difficult to solve. In fact, we can try to solve this directly. So what is the solution for this? Because it's a homogeneous equation, we can assume the solution is of the form e to the power x. But in this particular case, we can choose the solution to be sin h of x and cos h of x. That is a linear combination of sin h of x and cos h of x. In terms of the d operator, I could have written it as, forget the d operator, I could have simply used a solution of the form e to the power mx. So what do we have? So the derivation, the double derivative will give me m square e to the power mx plus 2 epsilon m e to the power mx minus e to the power mx equals 0. So we have m square plus 2 epsilon m minus 1 equal to 0, right? So m equal to minus 2 epsilon plus minus 4 epsilon square plus 4 by 2. That is the root. So these are the two roots. So m is either minus epsilon plus minus under root epsilon square plus 1. M is either the plus root or the minus root. So you could write the solution y as a to the power, so if I call this as m1 and 2, so m1x plus b to the power m2x. And we know that if a solution is of this particular kind, we could also write it in terms of sin hx and cos hx, because a linear combination of these two terms is also equivalent to a linear combination of those two terms. Okay, so let us simplify this further. So this becomes a e to the power minus epsilon x times e to the power square root of epsilon square plus 1x plus b e to the power minus epsilon x times e to the power minus square root of epsilon square plus 1x. We have these two terms, and now we can utilize the boundary conditions in order to find out the constants. So y0 at 0 is 0 and y1 is 1. So substituting x equal to 0, we have 0 equal to a, so this everything becomes 1 plus b. This implies a equal to minus b, and the second term, so 1 is equal to, substituting x equal to 1, a e to the power minus epsilon times e to the power. So let me call this square root of epsilon square plus 1 as alpha. So it's alpha x. So you're substituting x equal to 1 plus b e to the power minus epsilon times e to the power minus alpha x. So substituting a equal to minus b, so what do we have? E to the power minus epsilon times b minus e raised to alpha plus e to the power minus alpha. So we obtain b equals e raised to epsilon divided by e raised to minus alpha minus e raised to alpha, and a is simply minus of b. So the analytical solution that we obtain is y equal to simply this expression with the appropriate constants. So let us go towards plotting this. So let me create a new file. Let me copy the usual modules we will need. So let me create x equal to np.linspace 0 to 1. Let me take 20 points. Let me define a as, rather let me first define epsilon as 0.1, small number. Then what do we have? We have b, so let me define alpha as epsilon square plus 1 raised to 0.5. Let me then define b equal to np dot exponential of minus epsilon, or rather epsilon divided by e raised to minus alpha minus e raised to alpha. Alright, and a is simply minus b. So the solution y will be equal to a times e to the power minus x minus epsilon x. So np dot exponential of minus epsilon times x times a times np dot exponential of alpha times x plus b times np dot exponential of minus alpha times x. Alright, so now let us plot this. Okay, so solution looks something like this. Let me wrap everything inside a function which we can call later on. So I'll just take this whole lot, def analytical, and it will take the input x, epsilon and alpha, and it will evaluate all this, and finally it will return y. So epsilon we will pass, b alpha also we will pass. In fact, we just need to pass epsilon because alpha we can evaluate inside. Straightforward. So outside the function we'll just define this, and we'll say y equal to analytical x comma epsilon. Alright, yeah, great. So this is how the plot looks like, and well, in this particular case the equation was rather simple and we could find an analytical solution, but usually such kinds of parameters which we call as a perturbation parameter, and the reason we call it a perturbation parameter is because its magnitude is usually small, and the effect of that particular term is like a perturbation to some kind of a base term. Okay, and it will be clear why it behaves like a perturbation on top of some base solution once we do the expansion. But okay, for now we need to remember that you will have some kind of a base solution, and if that perturbation parameter were to be zero, okay, if this particular parameter epsilon it were to be zero, you would obtain y double prime minus y equal to zero. And so the base solution is sort of y double prime minus y equal to zero. But the moment you have a non-zero epsilon, but small, the solution will be sort of some correction to this base solution, because the limiting condition of zero epsilon, you will have a solution which is like the base solution. So we're not going to the specifics of regular perturbation, but in general what I'm about to show, it will work for a host of equations, and eventually you'll see that you can avoid doing very complicated analytical solutions but obtain very nice approximations to those analytical solutions. Okay, so let me grab this equation and let us begin with this. So this is subjected to y0 equal to 0 and y1 equal to 1. So let us make an assumption that we can represent the solution y as a series of y0 plus epsilon y1 plus epsilon square y2 plus order epsilon cube, meaning each successive term is of a decreasing order of magnitude. And the fact that we could write the solution in this particular form automatically assumes that each of these terms, y0, y1, y2, they are of order 1. So the order of this entire term is not governed by the order of y1, y2, y3 and so on, but it is governed by the prefactor epsilon, right? So the order of magnitude of this is expected to be order epsilon, not order epsilon square or something. If it were to be order epsilon square, we would have to rescale y1 so that the orders of each successive terms are preserved. And first of all, it need not be even epsilon square, it could be epsilon log epsilon. There can be a whole variety of gauge functions, but in this particular case, we observe that the equation does have a floating epsilon over here, and in this particular case, it works out. But usually, the choice of such an expansion has to be motivated to the physics of the problem. And some intermediary scalings that may arise because of considerations from the governing equation or the boundary condition that will give rise to a natural sequence like this. But I digress, in this particular case, it will be quite straightforward. So now let us take this particular expansion and substitute it over in this equation. So what do we have? So the first term is y double prime. So y double prime will be y0 double prime plus epsilon y1 double prime plus epsilon square y2 double prime plus order epsilon cubed. What about the second term? So it is twice epsilon y prime. So this will be what? So let me first write down what epsilon prime will be. It will be y0 prime plus epsilon y1 prime plus epsilon square y2 prime and order epsilon cubed. But now if we multiply everything by epsilon, what will happen? Well, it will look something like this, where This will now be this will now be epsilon, this will now be epsilon square, this will now be epsilon cubed, and so on. So in the term involving epsilon times y prime, there is no term which is devoid of epsilon. The sequence naturally starts with the lowest order of magnitude being epsilon. So now I need to multiply 2 as well. Well, that's straightforward. Alright, what about the last term? This is minus y. And that is simply y naught prime, not prime, minus y naught minus epsilon y1 minus epsilon square y2 and so on. So now let us add all of this. So we have y double prime plus 2 epsilon y prime minus y, and this will be, let us now write the right hand side in terms of various terms collected in orders of magnitude of epsilon. So epsilon to the power 0 has y naught double prime minus y naught plus epsilon to the power 1. So this particular term will have y1 double prime plus 2 y naught prime minus y1. Epsilon square will have y2 double prime plus 2 y1 prime minus y2 equal to, so not equal, and so on, plus order epsilon cubed and so on. So through this particular exercise, we are able to form an entire hierarchy of equations of order 1, order epsilon square, and so on. Right? We are able to form a hierarchy, and because this will be equal to 0, each of these terms have to be also 0, meaning y naught double prime minus y naught has to be 0, y1 double prime plus 2 y naught prime minus y1 has to be 0, y2 double prime plus 2 y1 prime minus y2 has to be 0. But what about the boundary conditions? Well, that's also straightforward to do. Let us write down the boundary condition. So what do we have? Y naught at 0, 0, and not y naught. Y at 0 is equal to 0 and y at 1 is equal to 1. So similarly we can write over here y naught at 0 plus epsilon y1 at 0 plus epsilon square y2 at 0, all this is equal to 0, and we can write y0 at 1 plus epsilon y1 at 1 plus epsilon square y2 at 1 equal to 0. So now if each of this is equal to 0, if each of this is equal to 0, then we equate all the terms. So this naturally implies, so all this naturally implies y0 0 is 0, y0 y1 at 0 is also 0, y2 at 0 is also 0, and so on. So all the hierarchy of boundary conditions. So this particular equation is an equation for y naught. This particular equation is an equation of y1. And why is it not an equation for y naught? Because once we've obtained a solution for y naught, we would substitute it simply over here, right? And what are the boundary conditions which this equation is subjected to? It is y naught at 0 equal to 0, and from this written this 0 by mistake, has to be 1. So this implies y naught 1 is equal to 1, but it implies y1 of 1 is equal to 0, y2 of 1 is equal to 0, and so on. Okay, alright, so that means that this equation is subjected to y0 1 equal to 0. So y naught at 0 equal to 0, y0 1 equal to 0. So let me write it down once again over here. So at order 1, we have y naught double prime minus y naught equal to 0, subjected to y naught 0 equal to 0, and y0 1 equal to 1. What about the equations at higher order? Order epsilon, y1 double prime plus 2 y0 prime minus y1 equal to 0, subjected to now y1 at 0 will be 0 and y1 at 1 will also be 0. So y1 at 1 is equal to 0, y1 at 0 is also equal to 0, y1 at 1 is also equal to 0. So this is called as the base equation, which satisfies actually the base boundary condition. But the perturbation equation does not satisfy the base boundary condition. It satisfies equal to 0 because it is like a perturbation to the main equation. And you can have a separate case where you are dealing with domain perturbation techniques, where not you're not motivated through the Gaussian equation, but rather by the nature of the boundary condition. But that's a completely different story. Here we have the Gaussian equation, which is split into the base equation and the perturbation equation and its higher order perturbation equation as well. And this equation will also be satisfying this. Okay, so the chain or the process hierarchy is first find out y0 using this, then find out y1 using this, and find out y2 using this, so on and so forth. You can keep doing this, but usually you will see that after a few terms itself, you've obtained an approximate solution of sufficient accuracy. Well, how do you know it's of sufficient accuracy? For that, you need to know asymptotic analysis. But over here, we're gonna take the leap of faith and hope that the solution satisfies the solution. The approximate solution also satisfies the analytical solution. So let me, oops, yeah. So let me encode this. Let us see how well this works. Well, before going into coding, we need to find out the solutions. So this is what y0 double prime minus y0 equal to 0. The solution is obviously y0 equal to a e to the power x plus b e to the power minus x, or equivalently we could write the solution as sin h and cos h, because when the basis functions are e to the power x and e to the power minus x, you can equivalently cast it in the form of a linear combination of e to the power x and e to the power minus x, which is sin h and cos h. This is a sin h of x plus b cos h of x. Because okay, so you can verify that this satisfies this equation. And now the boundary condition, the first boundary condition gives 0 equal to b and y0 1 equal to 1. So 1 equal to a sin h 1. So a equal to 1 upon sin h 1. So the solution for y0, it's gonna be sin h of x upon sin h of 1. So now let us go to the computer and try to plot this 0th order solution. So we have y as this, y0 equal to np dot sin h x divided by np dot sin h 1. So we're gonna put a label analytical, right? So let's see what we have. Not bad. So let me just change the line style to make it a bit more apparent. So the leading order solution we're gonna show as a broken black line, and this solution we're gonna show as a blue line. Well, blue, let me put as a red line. Okay. So now we see that the base solution, so this is the base solution. and the exact solution, which is the red curve, they are not far off, meaning the overall behavior of this equation is quite accurately represented by the base solution for small values of the perturbation parameter epsilon. And that is quite obvious. In fact, if I make it 0, they should exactly match. Great, they do exactly match. The perturbation parameter becomes zero point 0.5. Maybe they don't match so well. They don't match so well. And that this information is quite critical because while it doesn't match well, it does encode all the basic information of the monotonous increase and so on. So now you know that the next correction to y0, which is going to be through y1, it's gonna make the broken line approach the analytical curve. Wow. So we have this base solution which is arguably very easy to obtain, and now what we can do is use this equation to find out what y1 is gonna be. So let me write down the equation for y1. So it's y1 double prime minus twice y0 prime, rather plus 2y0 prime minus y1 is equal to 0. So now what is y0 prime? Y0 prime is cos h x upon sin h 1. So what do we have? Y1 double prime minus y1 is equal to minus 2 cos h x upon sin h 1. Right? So the solution for this, the homogeneous part. So y1 is gonna be y1 homogeneous plus y1 particular, and obviously the homogeneous solution is gonna be again a cos h x plus b sin h x. This is gonna be the homogeneous solution. What about the particular integral? Look, the particular integral has the functional form cos h x. So obviously the particular integral cannot have a form c cos h x. It cannot, because cos h x is already the homogeneous part, so it cannot have the same form, but it can have, and you can use various techniques that you have learned in a differential equations course. It can be of this particular form, and it is because the homogeneous and the particular, the inhomogeneous part has the same form as the homogeneous solution. So now let us use this form. So let us substitute in the equation. So what do we have? What is y1 particular prime? It's gonna be c cos h x plus cx sin h x, wow. And then we take another derivative. So y1 double prime 1p is equal to c sin h x plus c sin h x plus cx cos h x. So this is what? 2 sin h x times c plus cx cos h x. So now we actually have a form of 2 sin h x, which means that the solution has to be not of a cos h form, or it has to be of a sin h form. Well, yeah, it has to be of the form 2 sin h form. So once we take the derivative, this will become sin h x, this will become 2x cos h x. Now the second derivative will become, this will become cos h, this will become, again this will become cos h, and this will become cx sin h. So I request you to do this on your own and have a look. So this becomes 2c cos h x and this becomes cx sin hx. So this is essentially 2c cos hx. So now x sin hx times c is y1 particular. So this is y1 particular. So essentially we get y1 particular double prime minus y1 prime equal to 2c cos hx. Oh. But we already know that the particular solution has to satisfy this. It is minus 2 cos hx upon sin h1. So this is equal to minus 2 cos hx upon sin h of 1. Equating these two, we get an expression for c. So c is equal to minus 1 upon sin h1. Great. So now the solution is y1 homogeneous plus y1 particular. So a cos hx plus b sin hx minus x sin hx upon sin h of 1. Now the boundary conditions. So y1 is this. So y1 at 0 is 0. So 0 equal to, at x equal to 0, this is what a. Everything else is 0. And at y1 at 1 is also 0. So 0 is equal to, so a is 0. So this, what is this? B sin h of 1. And what is this? So minus 1. So b is 1 upon sin h of 1 and a is 0. So y1 becomes, what is this? Sin h of x upon sin h of 1 times 1 minus x. Whew, a lot of derivation, but yeah. So y1 is equal to 1 minus x times sin h of x divided by sin h of 1. So now with this, let me do plt dot plot x comma y naught plus epsilon times y1. Let me make it something like this. Label as y0 plus epsilon y1 well, let me, yeah, so what do we see? The red is the analytical curve, the broken lines are simply y0, and the broken dot lines are the corrections. So now look, because of the corrections, the solution matches quite well with the analytical solution. So if you are like me, you're not looking forward to analytical solutions every time, and you look forward to an approximate solution, regular perturbation is a great way of getting around things. You will obtain very easy hierarchical equations which will entail a very easy solution. Most of the times, it will help you get rid of non-linearities when the small term multiplies non-linear terms, right? So not always, but in many cases, it's quite beautiful how with just one correction. Now, of course, you can look at higher corrections. You have the solution for y1. You can now substitute this solution into the approximate equation for y2 and obtain the solution for y2 as well. And you can make a further tweaking of this. Okay. So let me increase the value of epsilon to 0.7. Even at 0.7, it matches quite well. At 1, the significant deviation. Well, this whole thing is not supposed to work for large values of epsilon. It's supposed to work for epsilon, the magnitudes of epsilon being much less than 1. So let me just put it back to 0.3. Matches quite well. So this is all about regular perturbation. Keep in mind that the order of the equation that we are starting with, that is this, it's a second order equation, because y double prime, and in this case the small parameter, that is epsilon, is multiplying something which is not the highest order term. Meaning, in the base case, we have epsilon equal to 0. So this is the base case. So base case is still something like this, which is still second order. So you're not sacrificing the order of the equation when you let epsilon go to 0. Now, all such things fall beneath the purview of regular perturbation. But if you had something like this, epsilon y double prime plus y prime minus y equal to 0. If we were to now, so this equation would still be governed by two boundary conditions. But now if we let epsilon go to 0, the base equation becomes this. So it's a first order equation, whereas the actual equation was a second order equation. Such kinds of things where you're causing a dropping of the order, they will not fall under the purview of regular perturbation, but they will fall in the purview of singular perturbation. And we will consider singular perturbation in our next lecture. Until then, it's goodbye. Have a nice day. Bye.